Good morning, everyone. I'm Evan Fernandez. Now that we have our mesh, basically have our geometry and everything, we need to mesh it. So before that, let's learn a little bit about the theory behind SnappyHexMesh. This is the basic outline of what SnappyHex will be doing. Basically, whatever is inside your SnappyHex dict file. First, what is SnappyHexMesh? Most of you might ask. It is a meshing tool that is used to generate a mesh over a 3D object. You can do it over a 2D object as well when the object itself is a complex one. It helps improve your simulation accuracy by refining the mesh around your object. You can add layers depending on how complex your geometry is and what is your application. So the meshing process is as follows. First, you have to generate a background mesh. Now, this is done with the help of block mesh utility within OpenFOAM, or you can use any other external mesher of your choice. Key things to note while doing a background mesh is it should consist only of hexahedral cells. That is, it should be a structured mesh with an approximate aspect ratio of 1 closer to the object itself, your object of interest. And your object has to intersect with the cells of the background mesh, obviously, meaning that your object has to be within that domain. Next, you have the actual geometry file. Now, in this case, in SnappyHex, there are a number of files that it accepts. The widely used one is an HTML file. So you can import an HTML file within the OpenFOAM domain and mesh over it. Now your modeling can be done again with an external modeler. In this case, in a particular case, we've used FreeCAD. Now your geometry will be located in your constant folder. Within that, there'll be a tri-surface folder. Within that, you will have your geometry folder. Now, once you have both of these two are put into the SnappyHexMesh. This is where your actual meshing process begins. This will control your snapping all the way down to your boundary meshing, refinements, removal of cells, and the addition of layers. Once this is done, then it will move to OpenFOAM. Basically, it will generate a mesh file that is easily readable by OpenFOAM itself. First now, moving to the background mesh. The background mesh, as mentioned before, it is generated with the help of the block mesh utility, consists of hexahedrals. And the cells, basically the cell size that you give of your background mesh is your base cell. Based on this cell size, your further refinements will happen. And this base mesh will cover your entire domain. Then you have refining your background mesh. Now, once you've generated your background mesh, closer to your object interest, you will have a finer mesh. That is done with the castellated mesh controls within your SnappyHex. All of these features, I will explain it once we enter the actual SnappyHex dict file. What this does is it will split your base mesh into smaller meshes depending on the refinement layer that we specify. And these edges of the object itself is extracted with the help of the surface features dict that will be in your system folder. So speaking of refinement layers, as mentioned before, you have your base level over here. This one is your block mesh cell size. Now, when we specify a level to it, it will split that base mesh into 4 equal parts. And then as we increase the levels, each of those 4 cells will be split into a smaller 4 cells. So that's how the leveling refinement levels work in SnappyHex. Now, once we've done a refinement level and you need to move to the next process, that is your removing of cells. In this process, all the unwanted cells, like if you want to do a simulation over an airfoil, all the cells within the airfoil will not be necessary because we're only calculating all the flow around it. So these unwanted cells are removed with the help of location in mesh keyword within that SnappyHex. What this location in mesh does is that you have to specify one specific point within your computational domain. Now, in this case, if I specify the point within this outer domain, it will keep all the cells greater than 50%, and anything that is lower than that within this object itself, it will remove them. Similarly, if I specify the point within this airfoil, it will mesh everything within this airfoil itself, and it will remove all the cells around the airfoil. So that way you can specify whether you want an internal mesh or you want an external mesh over your body. Then once the meshing removal, everything is done, you will have jagged edges. Like as you can see over here, these cells need to be refined a little bit. That is done with the snap mesh to feature. So this is done by the snap controls. This ensures that you get a good quality mesh that is usable in simple terms. Once that is done, the final step is to add a layer around your object of interest. What this does is it will smooth out the layers around your object, and any irregular cells that are there, it will basically just refine it around your object. So speaking of the case structure, this is a case structure that we are going to move into. You have your zero, constant, and system. Within your constant folder, as I mentioned, you have your try surface. This is where your metal, basically your HTL file will be there. Along with the HTL file, when you run in the system folder, the surface features dict, when we run this command, that is a surface feature, it will generate an e-mesh within your try surface folder, and it will generate another folder within your constant folder. I'll show all of that further. Once your surface features, this utility is done, we move to the SnappyHexMesh dict. This contains all your meshing parameters, all the refinements, cell size, anything that you have to specify, everything is done through this. And lastly, you have the mesh quality dict. This ensures that your mesh is in a usable range. And in this, we can specify various parameters to control your mesh quality. So let's move to the case itself. So in the case that we are going to run for the demonstration purpose, it's a coarser mesh. But to show basically what SnappyHex can actually do, I have run already a finer mesh. Let me open it in the terminal. Also, when you're generating a finer mesh, note that it will take a lot of time depending on the number of cells that you specified. Similarly, in ParaView to open the file also, it will take time. So keep that in mind when you're meshing a very fine case. Sometimes it might give you an error saying that ParaView isn't responding or something. Just click on wait to generate eventually. So we'll put a slice. Oh. Now in a conjugate heat case, we need a mesh that can capture everything inside the object itself as well as around it. So for that case, we made this mesh. Now, as you can see, this is the object, as John sir mentioned in his slide. Now, this mesh doesn't look that great. That is because it's like a visualization problem. This can be easily handled. Over here, you have your triangulate slice. If you switch that off, you will get a cleaner mesh. You can put this one on. So SnappyHex will look something like this. As I mentioned, hexahedrals are there. So this is your base cell size, what we specified in block mesh. And these are your refinements based on your refinement level. Based on your refinement level, it will break it down into the desired cell size. I'll show you one more view of your. Now, as I mentioned about adding layers, as you can see, the mesh closer to the edges are more refined as compared to the ones the center. This is good in capturing any curved objects if you have. So any complex geometry that you have is captured well with SnappyHexMesh. So now let's move to the actual case itself. So this is your clean case that you have. You have your zero folder. In conjugate, you will have two folders, that is your fluid and metal. Then you will have your constant. Within constant, as I mentioned, you have your try surface. This is where you copy and keep your HTL file. In this case, we have our metal HTL. These are all the remaining files that are there. Okay. In your regions property and all, you specify your fluid and air. Then you have your system folder. System folder, you will have three of these folders. You will have the mesh quality dict, SnappyHexMesh dict, and your surface features dict. So first let's go to the surface features dict. Within this, you specify over here your HTL file. Whatever is your HTL file name, you place it over here. What this does is it will read that HTL file and it will generate an edge mesh. That is done with the include angle. It will read how many features are there based on that, features as in your edge, and based on that it will refine those edges and will read them properly. Higher the number, you will have lower the number of features that it will capture. Whereas if you have a lower number, it will capture more features. Then over here you have your non-manifold edges. This is if you have more than two faces connected to each other, you can switch that on. If you have one connected face, you can switch that on and off based on your application. Then we have our actual file, that is your SnappyHex. Now, in your SnappyHex, first you have these three, that is your cache-latent mesh controls, snapping, and add layer. You can switch them on and off based on how complex your geometry is. Now, in this case, we'll keep them true as we need to just generate a simple mesh. Then, first we have our geometry section. Within this geometry section, first you will specify the name of your basically your HTL file. This file is your geometrical entity. Over here, I've mentioned each of the types that are allowed and read by SnappyHex to generate your mesh. So in this, we can see if you have HTL, you can import an OBJ file also. Then we have our type try surface. This is just a type of mesh it's going to generate. And you have your user defined name. Now this name is specified by us. In this case, I've specified as metal. If you don't specify it, it will default take it as metal and it'll put it as a region. So it will just rename it according to itself. So you'll have to just check that. But putting a user defined name is essential because further you will be using these names further. And as you saw in the refined mesh, we put in the final mesh that it was very fine. We've put a refinement box. Now what this does is, I'll just switch tabs. So what does this refining does is, suppose we have our object. This is our HTML. This is our HTML file, and this is our domain. Okay. Now, what the refinement box does is that it will specify a normal box around your HTML depending on the coordinate system that you specified. So now we specify this as refinement box 1. And if in case you want to specify a secondary box, you will specify this as refinement box 2. Now, so as mentioned before, you can rename it to anything that you want as long as you remember. So it's simple to just rename it as refinement box. Over here, we specify the upper limit and the lower limit of your box, that is in your minimum and maximum. As I mentioned, in this case, we put two refinement boxes. One is closer to the object itself, whereas the second one is a little bit farther from it. Once we're done with that, you move to the cache-related mesh controls. This is where you control your refinement parameters. Now, in the first one, you have your max local cells. This is the maximum number of cells allowed per processor. If your processor exceeds this number, it will switch from balancing to further before further refining it. Balancing is done further over here. So instead of refining it, it will directly switch to this level and it will move forward. The second one we have is your maximum global cells. This is the total number of cells in the entire simulation. The refinement will stop once this limit is reached, and this number is the cells, basically the overall cells without removal. So in the end, if you have a simple geometry in which you are going to be removing most of the cells, this number won't be the actual end cell size of your final file. Then we have the minimum refinement cells. This is your minimum cells required for refinement per iteration. This avoids excessive iterations. Now, if we specify this as a lower number, if the minimum number of cells are 5, and it will take the least number of cells, that is, if there are even 5 cells, it will start to do an iteration over it. So this is time consuming. So if you specify a higher number, it will take a group of cells and it will start refining over them. Then you have your max load unbalance, that is 0.10. This is the amount of load imbalance allowed per refinement. Now, what does max load unbalance do? It is the amount of load imbalance allowing per refinement. It refers to the distribution of computational workload entirely across all processes in parallel. So if we specify this as 0, it means that each of the processor is going to get equal number of cells to process. So what we do is we keep a little bit of threshold so that the processor isn't completely loaded, and it will have like a 10% give or take of cells up and down. That way it is. So this is where you specify that. Then you have your n cells between the layers. This is the number of buffer layers that will be between each of those refinement levels. This helps prevent a sharp discontinuity between different refinement layers. Now over here we specified 8. What this does is it will create 8 layers between each of the refinement levels. So it will be like a gradual change from one refinement level to another one, and won't be a drastic one. If you lower this number, it will be a drastic one. Depending on how you want it, you can specify that number. Then we move to the features part. This is where, as I mentioned, you have your edge mesh. Now this is generated with your surface features dict that we saw previously. And this one also we specify a refinement level. This now, as I mentioned before, refinement level of 4. So your base cell will be refined 4 times. So you'll have that much fine mesh. Then we have our refinement surfaces. Within this, we have refined our metal. Again, this is the name that we've specified. So that, as I said, if you do not specify a name, you will have to know how to write your name over here. So it's easier to specify just name, and then after that, use that same name everywhere in your file itself. Now, in the refinement surfaces, you have your refinement level. Now, this is your minimum and maximum refinement level. Then we have this one. Now, within refinement surfaces, you have 2 options, whether you want to do basically whether you want your mesh to be within the domain itself, basically within your object also, or you want it around your object. If you want it inside your object, like in our case, we need it within the object itself. So we specify cell zones and phase zones. The name that we specify is user specified. This will help you identify your cell zone that you've given. And then we have a cell zone. This is where you specify whether you want it inside a geometry, outside a geometry. Now, in case you want to do an external flow and you just need to remove some cells from within the object itself, that can be done with this patch info. Now you specify patch info, and in that you specify a type. The default type is wall, and you cannot specify anything else beside wall because SnappyHex will take it as a wall itself. That's how it works. So if in case you want to do an external flow, you can switch this on. In this case, we'll just switch it off. Then once that is done, you have your resolve feature. This one controls the amount of curves that is captured by SnappyHex. The higher the number, it will result in lower features. Whereas if you put a lower number, it will capture more features. That's why we specified a lower number. Then you have refinement regions. This is your region-wise refinement. In this one, we've put metal. Inside this, in refinement regions, you will have 3 types. That is your mode. In mode, you will have distance, inside, and outside. Now, in distance, it will specify the base level on basically your suppose you have if you have a base, your cell size, you specify that base, and then as you move away from the object, that size will increase. That is how your distance works. Whereas inside, you will specify a refinement level within the object itself, and it will basically refine the mesh within itself. Outside, it will do the exact same thing, but in the opposite direction. So in this case, we put a metal. Each of the refinement boxes, we've specified it to mesh within itself. So it will refine each of those boxes from inside. Then, as I mentioned before, location in mesh. This is the point where you will specify in your domain. This will determine whether you want an internal mesh or an external mesh. So this point is quite important when you're specifying what kind of meshing you want to do. Then you have your allow freestanding zones. In this case, we put it as false. This one will handle your zones that aren't bound by the geometry. What this means is that suppose if I put it as true, it will keep these freestanding zones. That is useful when defining. So basically, if you want any isolated faces or any zones that are isolated from the object itself, if you specify it as true, that is that does. If you specify it as 4, if there are any freestanding zones that are not connected to the body itself, it will start to delete them or it will try to snap it. So this may cause sometimes an error, but most of the times if you have a simpler geometry, if you don't have any freestanding zones, it's easy to put it as false. Then you have your snap controls. This is where it will basically check your snapping and how does the snapping process go about. So in the first one, you have your N smooth patch. In this, we put 3. This will specify the number of patch smoothing iterations. Then we have a tolerance. Now, if your tolerance is less than 1, it is good for a finer mesh since it will try to take the closest cell and it will snap it onto the object itself. Whereas if you have a moderate mesh, 2 is fine. Anything above 2 is good for a coarse mesh because it will take any cells close to or any cells that are a little bit farther from the object and will snap it. So if your mesh is quite coarse, it's good to have a higher number of tolerance. Then we have the solver and n-solve iterations. This is the number of iterations that it will do to achieve or snap each of those cells onto your object itself. Higher this number, higher will be the mesh quality. You will have a better quality mesh, but it will take also a lot of time. So keep that in mind when you increase this number. Similar for the n relaxation factor iteration. This will also have a relaxation factor. Then you have your n feature snap iteration. This will specify how many iterations it needs to snap the features, that is any edge or any sharp angles that you have to the object itself. Similar with this also, higher the number, more amount of time it will take, but you'll have a better quality mesh. Then we have the implicit feature snap. Now in this case, we have it set to false. Now this determines whether you want to automatically have your object itself detected by SnappyHexMesh or you want to detect it by using that surface features extracting. So in case you want to automatically detect your object within the domain and mesh it, you can set it as true. Whereas if you set it as false, the explicit feature snap has to be set to true because it will start to search for an edge. If in case you have any sharp angles or you have a curve or something, this one will read the file that is generated, basically your edge mesh file that is generated by a surface features. And it will, even though it cannot find a proper edge, we specified an edge mesh, it will directly snap all of the cells closer to that edge itself, since it's already read by surface features dict. So it will say that there is an edge over here and it needs to be snapped. So that way you will have a more refined mesh closer to the edges. And then we have our multi-region surface snap. This determines where your snapping on multiple regions. This is essential when you have multi-phase regions. If you set it to true, it will mesh individually each region. Whereas if you have a simpler geometry like our case, it's set to false because we do not have that many regions that need to be meshed simultaneously. Then once you're done with the meshing part of basically the cells and everything, you add a layer. So in your add layers control, it will add whether you want to add a layer around your object itself. So you have your relative sizes. This is again set to false. This one will determine the layer size relative to the cell size. Then we have our layers. This one will specify the layer addition to a particular patch. Now in this case, we have again used our metal. Around that, we specified to put two layers of meshing, basically two cell layers around the object of interest. The expansion ratio is similar to grading. It will determine how much growth you want from the layers as you move away from the object. Then you have your final layer thickness. This one, it sets your final layer thickness as a fraction of the cell. Now, suppose you set a target thickness of the final layer as a fraction of cell. Suppose you put this as 0.9. For example, if you have a local, basically your base cell size is of 1 mm, the final layer thickness will be of 0.9 mm thickness. Basically, you can either use the final layer thickness or you can use the first layer thickness. So the first layer thickness is in which we manually set the thickness of the first layer itself, depending on your base level. If this is within that range, like if it is smaller than your base level, then it will achieve. If it is above that level, then it will not generate any refinement layer around your object. Then you have your minimum thickness. This will again determine the thickness needed around your object, which will generate your layers. Then you have your n grow. In n grow, we specify it as 0. Now, n grow will mark your neighboring cells, any cells that are around your object, for a potential layer addition. Now, in this case, we set it as 0. Suppose we specify it as 2. What this does is it will take two layers, basically two cell distance above your object, and it will potentially keep that in mind that there are these two cells. In case we need to mesh around the object itself and add a layer, it will take those two cells. So it will potentially add a layer around your object. So this is where you can specify how much you want. Then we have our feature angle. Again, like previously, this specifies the angle, basically the edge. Lower the number, it will capture more of the features. Higher the number, it will capture less. Then your split feature angle. This one will control your growth over edges. These are the number of snapping iterations and your relaxation factors that will be in play when you do your snapping, your smoothing, normals, everything. Then we have, this one is important, max face thickness. So your max face thickness, it will be, this is what stops your layer growth on highly warped cells. And you have this max thickness to medial ratio. This one will smooth the growth with ratio thickness to medial. What this means is that it will ensure a smooth transition between layered and unlayered regions to maintain a mesh quality and avoid distortion. Now, if this number is high, it is crucial for boundary layers where you need, like for an external flow, you need the layer closer to the body to be well refined. So if you have something like that, you can specify a higher number. Whereas if you have a smaller number, it is good in narrow regions since it will not refine it that much, but it is moderately okay for most of the case. The default range of this is between 0.3 to 0.5. So basically you can use it at the default region, the default range as well. And then you have your minimal axial angle, that is a 90. This controls your layer addition where mesh aligns with the edge. This one, your N buffer cells no extrude. This one will create a buffer region for any new layer terminations. This and then finally you have your N layer iteration. This is your overall iterations for layer addition. Again, this one, higher the number, better quality mesh, but you will have more time. It will take more time to mesh the whole thing. Then we go to the mesh quality controls. This is where we include our mesh quality dict. This is a dict that is in your system folder. I'll show it in a second. In this one, we can specify the number of iterations that is there to smooth and to generate a good quality mesh. And then we have the error reduction. Now this amount is basically for displacing all the error points. Now suppose you have an error of 1 mm and we specify this as 0.75, it will move a mesh to a distance of 0.75 mm per iteration. So it will basically refine it slowly based on your iteration numbers to the desired number. So it won't be a drastic change. Then we have our write flags. This one will control what is written during your meshing process within your terminal. So in this case, we wanted to write the scalar levels, the layer sets, and the layer fields. Basically, it'll give you an output on your terminal itself. And then we have the merge tolerance. This is the fraction of overall bounding box of the initial mesh. So this is the mesh quality dict. This is where you specify the basic parameters that you need for a good quality mesh. This can be changed according to how you want to use your actual object itself. So as I mentioned before, first you have your block mesh. This will generate your base mesh. So in this one, we specified a simple box, a cube, since we have a three-dimensional body. This is a simple cube. We specified the vertices, the blocks, and this we've given the cell size. The edge grading, there's no edge, and then we put our boundary conditions. Now in this, we have the left-hand side, that is your fluid inlet, right-hand side fluid outlet, and anything around it is the walls. So once you do this, we move to the snappy hex. Within this, we specify each of those parameters. So the main parameters that you can change is the metal. First, you specify your HTL file. Then you specify your refinement box. If you want to add a refinement box, you can. If you don't want to, it's basically depends on your application. Then we have a cache-related controls. Over here, you specify the local number of cells you want, and then you specify the global cells. Note that higher the number, more time it will take. So keep that in mind. You can specify your refinements and everything over here. Then you specify your features. Now, since we've put over here in the lower end, we have clicked on true for explicit feature snaps. So if this is true, make sure that your eMesh file, that is your edge mesh, is there in your features file, since it will be reading this one to generate a good quality mesh around your edges. So that this is important if you're using the extrude external one. Then refinement features. In this, you can basically, if you have an internal or external mesh that you specify over here, your resolve and everything, then you have your regions where you specify this. So now once these factors are done, there are two ways to do meshing. One is in your series configuration, and other one is in your parallel configuration. So these are the set of commands that you will be running for if you're running it in serial. If your geometry is simpler and your mesh size isn't that large, you can use it in a serial format. Whereas if you have a finer mesh, it will take time to run it. So I'll show you how to run it in a parallel configuration. So first you go to the file, then you open the terminal. First you run the block mesh command to generate your base mesh. So once this is done, I'll show you how the block looks. Paraform. So this is a block that we have. Note that there's nothing inside it for now, since we've only generated a simple block mesh, a block using block mesh. Now, once that is done, you run the command surface features. Now, note that surface features, if you're running OpenFOAM 9, this is the command. Whereas if you're running a higher, basically if you're running the .com version, you will have surface feature extract. This is the option for OpenFOAM if you're using 2212, 2212, 2312, any of the higher variants. Now in this case, we're using OpenFOAM 9, so we will have surface features. Now, as you can see, it has read the file, basically a HTML file, and it has generated a eMesh file. Previously, there was only a metal HTML. Now there is an eMesh file, that is your edge mesh. Along with that, it has also generated this file, that is your extend features edge mesh. With this one. Once you've done this, now to run it in parallel, we need to decompose your block mesh. So we'll decompose the whole domain. Now this one is set to 4. Once you've done that, you will run SnappyHex in parallel. Now again, depending on your cell size, you will have this process will take time. So keep that in mind. Now, since we are going with the coarser mesh, it should run faster. To make the process faster, we'll change some parameters within our SnappyHex. Okay. So we'll lower these local and cell sizes. So again, we run block mesh. Once we've done that, we will run surface features to extract the edges, decompose. And then we'll run SnappyHex in parallel. So by the time this process is running, we will check if there are any questions in the chat box. Is there any other method than location to retain the mesh? Like in multi-region form, it is tedious to find all points. Okay, so you're trying to ask how are we specifying the mesh within the domain itself and the object also. Okay, so that is done over here. In your metal, we specify the cell zone and we specify a phase zone and we specify this inside. So what this does is it will generate a mesh within your object itself. If in case you do not write this, it will just generate a mesh around it. It will remove all the cells from inside the object and it will term it as a wall. That is how you do. Hope that answered your query. Then did you use 4 processor for parallel meshing? Yes, in this system, currently I'm using 4 processors for running the simulation. How SnappyHex is compared to CF mesh? I'm not sure exactly what is CF mesh. I'll have to look into that. And do we have any limitations on the mesh count? The mesh count as in, are you trying to ask whether you have a limitation on this, on the cells? So there's no limitation as such, but if you specify a higher number, obviously it will take a lot of time to mesh your actual geometry. So you have to keep that in mind, because if you go with a very fine mesh, your computer should be able to handle it and you should have the time. So usually a moderate number should do the job. Let's check the mesh. This is still meshing. Okay, one more question is there. How can we perform computation on HPC? How can we connect to HPC?
For HPC, you need to set it up like that. Okay, because there will be multiple nodes which will be communicating with each other. Again, the communication can be through either it will be MPI, you will need to submit your runs using. So the communication can be using Slurm or what was the other option? But so for that, see, you need to have, means OpenFOAM has to be installed in a certain way. Generally on the main node, you will install OpenFOAM in the shared folder so that all the subfolders have access to it. Then you will also need to write a script, like how you do in ANSYS, so that that communicates. You need to basically submit what is called like a job on the HPC. So there will be one job scheduler. Job scheduler will take that job and then distribute it to the number of nodes. So there are steps to do that, and I think not exactly tutorials. You can read it in forums of how to install that. We have done something like that, and we are working on it. So right now we have a system in which we run what you can say job on a cluster with 5 nodes. We are planning to increase it to 20, but that is not something that what you can say we can demonstrate now in the interest of time, and also it is what you can say it's a very specific topic. Everybody will not need that. So this we are basically interested. This is only for people who are in the intermediate level. We want to bring them up to a level where they understand what is happening. But HPC again, it is specific. So generally for institutes, say like in IITs, NITs, wherever the HPC facility is there, you need to install what you can say OpenFOAM in that way. You can contact your system admin for that.
Okay. So the meshing process is done. Now, since we've run it in parallel, you need to reconstruct the mesh. So for that, you have the command reconstruct par mesh, and you will only do the latest time. And we want to specify to generate the mesh within the constant folder. So we have constant. Now I'll show you the mesh. Now, since we've gone with a coarser mesh, we'll slice this. There is some visualization problem. We'll just delete this one again. Slice. Okay. So I'll show you the case that is already run. This one is having some visualization problem. So now since we've gone with a coarser mesh, it did not add a refinement layer. Now that is the reason I'll show you. You're supposed to specify in your add layers, your thickness and all of these parameters have to match your base level. Now, if your base level mesh is small enough and your refinement layer you're trying to add is greater than that, it won't add any layers. So make sure when you're adding layers and all that it is well below that value to generate any layer. In the fine case that I showed you previously, in that one, the refinement level of the base, basically the add layers, the layer around the edges of that object was smaller than the base level. That's why it was able to generate a clean surface, clean layer around the object of interest. Once you've meshed and everything, since we have a conjugate heat transfer, you need to split that mesh into a proper fluid and into a proper solid. So to split that mesh, you have the split mesh regions into cell zones. And over here, we are specifying default region name as fluid. Why we are doing this is because if we do not specify it, it will just add a name as region 0 or something. So it's better to just add a region name. In this case, we've added fluid. Now, as you can see, in this case, there is no polymesh. Once it begins to do the splitting mesh, it will basically break down the mesh into a proper fluid and a proper solid, and it will add those polymesh files into each of those file structures. Okay, until the splitting mesh is done, now Johnson will explain the conjugate heat transfer case structure.